Today I want to talk about the acid-base chemistry of amines, both alkyl amines and aryl amines. And I also want to talk about the acid-base chemistry of alkyl alcohols and phenols, since there is usually a lot of confusion for students in relation to terminology and when they should be looking at the basic character of an amine or a conjugate acid, conjugate base chemistry. They get very confused with these terms and what the pKa's mean and which pKa they should be looking at. There tends to be a lot of confusion here. So I've tried to make a few pages and I'm going to explain them to you. So up here at the top I have both an alkyl amine and an aryl amine, and I'm showing up here at the top both of these acting as acids to produce their corresponding conjugate bases. Now, in order to do this favorably, you need a very strong base, and there aren't a lot that could do the job for you. The ones that could do this favorably would be deprotonated alkanes or deprotonated alkenes or deprotonated aromatic rings. Those are the ones that could actually do this for you in a favorable manner, but most of the time this is not going to occur. The pKa of these acids is such that you can see that they are very weak acids. They're quite high. And so this is very unfavorable chemistry. We don't typically see amines acting as acids, though it is possible. What I am going to talk about, though, is the conjugate base. These are strong bases, but we want to talk about the degree of strength. And in order to do that, I have to talk about things in terms of pKa's. Remember that pKa's are talking about acid dissociation ability. It hasn't got anything to do with the ability to be a base. But we don't use pKb in organic chemistry a whole lot. We use pKa's. So we have to talk a lot about a base's correlating conjugate acid in order to understand the basicity and nucleophilicity of these negatively charged species, or in some cases neutral species. Now, amines, of course, can be bases, and you're actually going to see them more in this realm of chemistry. They are able to pick up protons from varieties of sources to make up their corresponding conjugate acids. And these conjugate acids are weak, but they're not as weak as the ones I was talking about previously, where the amine is the acid. The conjugate acid strength for an alkyl amine that has been protonated is around 10, and that for an aryl amine that has been protonated usually is somewhere between 4 to 6. In the case of aniline becoming protonated, the conjugate acid's pKa is 4.6 exactly. Now, as we go through this discussion, I'm going to pull up a few more pages and talk about conjugate bases in terms of their, I'm going to talk about bases in terms of their conjugate acids. Okay, so this would be the conjugate base of an aryl amine when the amine is acting as the acid. So this would be the conjugate base. This would be a very strong base. And as I've drawn up here for you, you can see the resonance delocalization of the negative charge through the aromatic ring at the ortho and para positions. Now, this delocalization can be enhanced, meaning that you can cause this nitrogen to want to give up its lone pair even more so to the ring, or it can be decreased, meaning you want to give less electron density into the ring, depending upon what other groups may be present on the ring and where they may be present. Now we see the greatest enhancements at the ortho and para positions because that's where the extra electron density is actually going to in these resonance structures. So what I have here for you is an example of the same type of base with an electron donating group. I'm going to call that an EDG group. It doesn't have to be the one I've shown here. Now, as you can see from up above, there is extra electron density at this particular carbon, the one that is para from the nitrogen. And as a result of that, there is negative character from the delocalization of that lone pair next to another electron donating group. So this will cause the conjugate base to be a little bit less stable because you've got more negative character right close to each other. And so the correlating acid, its conjugate acid, which would be the arylamine, will be similar in pKa to aniline. It should have a pKa around 30, or maybe even a little bit greater, meaning that it would be a weaker acid. So these electron donating groups are going to make the amines a little bit weaker acids from the get-go. In other words, these types of acids right here, they would probably be a little bit weaker if you have an electron donating group on the ring, and the conjugate base therefore is a little less stable. Now, if you put an electron withdrawing group on the ring, you're going to get an extra resonance structure, like I have here with the nitro group at the para position. You would get the extra resonance structure only if it were ortho or para. Meta will still experience an enhancement, but it won't get an extra resonance structure. But since you get an extra resonance structure, this means that the conjugate base of the amine would be weaker. It is more stable because there is more resonance delocalization of the negative charge. And if the base is weaker, its corresponding conjugate acid, which would be the arylamine in this case, would become more acidic because the base is weaker. Therefore, the pKa will be less than 30. And again, I'm talking about something like this. So if you have an electron withdrawing group on here, the pKa of the amine as an acid would actually go in that direction. It's going to become a stronger acid here. All right. Next up, we're talking about the amine as a base, which is the way we typically talk about amines, since they are usually bases, or if they can't be bases, they tend to be nucleophiles. So there would be some proton source available to this amine, be it an alkylamine or an arylamine, so that you can form their corresponding conjugate acids. Now for an alkylamine, the correlating conjugate acid tends to have a pKa around 10. And for an arylamine, the corresponding conjugate acid tends to have a pKa somewhere between about 4 to 6. In this particular case for aniline, the pKa of its conjugate acid is exactly 4.6. So again, we are going to have to talk about the conjugate acid pKa to understand the basicity of the amine when it is actually the base. So we can draw resonance structure showing that the nitrogen is an electron donating group into the ring, and again it would be donating that extra electron density onto the ortho and para positions by resonance. So it is an activating group to one of these rings if you're talking about electrophilic aromatic substitution, for instance. But what happens to the basicity, not the nucleophilicity of this nitrogen? Again, you got to think about what the term means. If something is being talked about as a base, we're talking about its ability to be a proton acceptor. In other words, this lone pair up here needs to be completely available to pick up a proton. We aren't talking about this delocalization through the ring. If it's a better base, we're actually minimizing this delocalization of electron density through the ring so that the lone pair is more available to pick up a proton. So what happens when we put an electron donating group on the ring, like an alcohol? This is actually quite helpful. It'll make this amine more basic. And this is because the oxygen will also be able to donate electron density into the ring at its ortho and para positions. And since it will also be donating electron density into the ring, you have a helper in the electron donating group. And as a result of that, the nitrogen doesn't need to donate its electron density as much into the ring because there's another helper. And if that lone pair doesn't have to be donated into the ring quite as hard by resonance, that lone pair will be more available to pick up a proton, making it a stronger base. And if this becomes a stronger base, that means that the corresponding conjugate acid is weaker. So the pKa of the conjugate acid will be greater than 4.6, which is aniline's conjugate acid's pKa. That will mean that those acids are weaker. And again, we are talking about the conjugate acid of these bases. We're talking about a species like this when we're talking about the pKa. So if you put an electron donating group on this ring, especially at the ortho and para positions, though you still see this with meta, the pKa of the corresponding conjugate acid will be greater than 4.6 because they will be weaker acids. Now what happens if we put an electron withdrawing group on the ring? Well, if you do this, you're going to get an extra resonance structure from the ones I showed up here above. So now there's a fourth one that will look something like this, depending on what your electron withdrawing group is. But it's going to suck more electron density out of the ring toward this electron withdrawing group. So the lone pair is going to be more strongly pulled away and into the ring, meaning that this lone pair is less available to pick up a proton and be a base. And since it's going to therefore be a weaker base, the corresponding conjugate acid will need to become stronger, which means the pKa of that conjugate acid will be less than 4.6. And again, I'm talking about something that looks like this. So if you put an electron withdrawing group on the ring, you're going to produce a conjugate acid that is stronger. And you're going to notice that this effect is enhanced at the ortho and para positions because you get that fourth resonance structure. Meta won't get a fourth resonance structure, but it still will cause the conjugate acid to become stronger. Now, the last group I want to talk about is phenol in chapter 22. I didn't have time in class to draw all this out on the board, and some of you looked very lost when I talked about this, so I thought we'd do this again. All right, so a normal alcohol, when it acts as an acid, is a weak acid. It has a pKa of about 16, which means that its corresponding conjugate base is considered to be a strong base. This is kind of our line of demarcation between strong bases and weak bases. And these types of bases, these alkoxides, have a localized negative charge on oxygen. And they are very good bases, and they're pretty decent at picking up protons in solution. Now phenol, which is an aryl alcohol, has a pKa of about 10. And that is because when we pull this proton off to come to its corresponding conjugate base, phenoxide, this negative charge is delocalized in the ring through resonance. This is what it looks like. We can draw 4 resonance structures showing the delocalization of this lone pair into the ring. And as a result of that, the phenoxide is a more stable base than an alkoxide. And again, the reason for that is because we have resonance structures here, whereas when we're talking about the alkoxide type bases, there is no resonance delocalization. So these are stronger bases and these are weaker bases. Now what happens if you put an electron donating group onto the ring? Well, this nitrogen, as we were talking about a moment ago, is actually an ortho-para director because it is donating its electron density onto the ortho and para positions. And because we're getting more electron density into the ring, this isn't really helpful. You've got negative charge delocalized by resonance by both groups, and so this doesn't really cause much to occur. The base might actually be a little bit less stable, but not significantly so. Most of the corresponding conjugate acids are going to have pKa's very similar to that of phenol, or maybe just a little bit higher than the pKa of phenol. So again, if we put electron donating groups on these rings, when we talk about the ability to be an acid, they're still going to be right around 10. They're not significantly different than 10. You might see small variations, but most of them are still right around 10 if you have electron donating groups on these rings. Now, what happens if you put an electron withdrawing group on the ring? Well, you get a fourth resonance structure if the electron withdrawing group is on the ortho or para positions. Meta would still be affected, but you wouldn't get this fourth resonance structure. So 4 resonance structures where we're showing delocalization away from the oxygen for a total of 5. That means that it's more stable. This would be a more stable conjugate base. And if it's more stable, that means that you would have had to have a conjugate acid which is the phenol, and it would have been more acidic. So if this type of base is more stable, we're talking about this acid being therefore stronger because this is more stable, meaning it's a weaker base, stronger acid. And if it's a stronger acid, the pKa is going to be less than 10. And again, you're going to notice more significant effects when those electron withdrawing groups are on the ortho and para positions. I hope this video helps a little bit with some of your issues with acid-base chemistry and understanding when we're talking about phenols as acids, or if we're talking about their conjugate bases, but especially this issue with when an amine is acting as an acid or when the amine is acting as a base. You're going to need to understand pKa's for the acids, be they the acid itself or the conjugate acid of the amine. And you need to know if they are becoming weaker or stronger just by understanding trends.